Hello everyone, welcome to LICD Lecture 40F. Today we are going to analyze a practical differentiator in frequency domain, and then we will build up on the frequency response of a practical differentiator. Okay, so let us start. So a practical differentiator using Opamp circuit is shown over here. Here it has two additional components. One is capacitor CF, which is in parallel with RF, and another is resistor R1, which is in series with C1. So these are the changes from the ideal differentiator circuit diagram. Now let us observe few things before we move on to the derivation. Okay, so first, the parallel combination of RF and CF is called as ZF. So that ZF will be given by RF parallel to 1 upon S into CF. And if you evaluate it and algebraically solve it, you will get ZF equal to RF divided by 1 plus S times CF into RF. Now, similarly, Z1 is a series combination of R1 and capacitor C1. So Z1 will be equal to R1 plus 1 upon S into C1. So that's the value of Z1. If you solve it, you will get Z1 is equal to, if you rearrange the terms, Z1 is equal to S times R1 C1 plus 1 divided by S into C1. So that's the value of Z1 and ZF. Now certain observations before we proceed. So this practical differentiator is, you know, eliminating the problem of or reducing the problem of stability and high frequency noise by adding two components R1 and CF. Let us analyze one by one. So the problem of high gain at high frequency is overcome by generating an artificial corner frequency by connecting the capacitor CF in parallel with RF. The second problem of the input impedance becoming very low at high frequency can be overcome by connecting a resistor R1 in series with capacitor C1. So with this at high frequency, even if the reactance offered by the capacitor becomes zero because of high frequency, then also the minimum impedance is R1 for the circuit. Okay, so this will solve that input impedance becoming very low at higher frequency. Okay, so next we'll analyze the practical differentiator circuit in frequency domain. So for this, we need to find the transfer function V out of S divided by V in of S. So as you know, this system looks like a inverting amplifier, general inverting amplifier system, wherein the gain of the system is minus ZF divided by Z1. So that's exactly what we will write over here. V out upon Vs is equal, V out of S upon V in of S is equal to minus ZF upon Z1, which is equal to, in the numerator we have RF divided by 1 plus S times CF into RF, and in the denominator we have 1 plus S times R1 C1 divided by S into C1. If you rearrange the terms, you will get that is equal to minus S times RF into C1 divided by 1 plus S RF CF into 1 plus S R1 C1. So in this equation, let's consider RF CF to be equal to R1 C1. If we do that, we can rewrite the expression of the V out of S upon V in of S as equal to minus S times RF C1 divided by 1 plus S times C1 R1 the whole square. And this is given by equation number 1. Now, if you want to convert this into a frequency domain, we need to substitute S equal to j omega in equation number 1. Hence, we get V out of j omega upon V in of j omega is given by minus j times 2 pi f RF into C1 divided by 1 plus j 2 pi f R1 C1 the whole square. Now, we rearrange this term smartly so that in the numerator we have minus jf divided by 1 upon 2 pi RF into C1. We will shortly understand why we do this. And in the denominator, we'll smartly write the equation as 1 plus j times f divided by 1 upon 2 pi R1 C1. And we complete this bracket and the square. So why we do this, we will understand now. So let's say that the gain of the system, that is the differentiator in frequency domain, will be rewritten as minus j times f upon fa divided by bracket open 1 plus j times f upon fb bracket close the whole square. So what is FA and FB? FA was 1 upon 2 pi RF into C1. FB is given by 1 upon 2 pi R1 into C1. And FB is 1 upon 2 pi RF into CF. Okay, so that is, we call it equation number 3b. So this equation number 2 is really the transfer function of a practical differentiator in frequency domain. Now, let's take the magnitude of it. So the mod of A will be F upon FA. In the denominator, we have under root of 1 plus F upon FB the whole square, and the bracket square of the under root. Fine. So it can be written in a modified form as follows. Mod of A will be equal to F upon FA divided by square bracket open 1 plus F upon FB square bracket close the whole square. So you can rewrite this in terms of decibels as mod of A will be equal, in dB will be equal to 20 log to the base 10 F upon FA minus 20 log to the base 10 1 plus F upon FB the whole square. So this is equation number 3a. So equation number 3a and 3b will tell us that the gain of the differentiator depends upon the frequency of the input signal. Now just one point from equation number 2 is that this equation number 2 suggests that it has 1 0 at FA while it has 2 poles at FB. So that's the thing which I wanted to clarify. Now, let's consider the values of R1 as 1.59 kilo ohms, C1 as 0.1 microfarad, RF as 15.9 kilo ohms, and CF as 0.01 microfarad. So let's plot it in LT spice and let's check what are the results. Okay, so over here, this is my practical Opamp differentiator circuit. We have CF as 0.01 microfarad, RF is 15.915 kilo ohms, R1 is 1.5915 kilo ohms, C1 is 0.1 microfarad. So these are the values for the components used inside the practical differentiator circuit. Also, we can easily calculate the value of FA, which is 1 upon 2 pi RF into C1, which will be close to 100 Hertz. And FB will be 1 upon 2 pi R1 C1, which will be close to 1 kilohertz. Now you can see 3 circuits over here. The first one is the open loop op-amp. The second one is the practical differentiator. And the third one is the ideal differentiator. Actually, we want to compare how will be the responses looking like. So let's simulate. We'll go to run, simulate, and go to run. And then we will be plotting the output for the open loop op-amp, ideal differentiator, and at the last we will plot it for, just wait. Next we will plot it for practical differentiator, and at the last we will plot it for the ideal differentiator curve. We'll expand this and we'll delete the phase plot. Okay, so this graph, this is the frequency response comparing open loop op-amp, ideal differentiator, and practical differentiator. As you can see, the orange color curve is my open loop frequency response, green color is my ideal differentiator, and the blue one is the practical differentiator circuit. Now let's check this number whether it is 60 dB or no. So yeah, I think it will be close to minus 60.00 dB. So it's minus 60 dB. Let's check the frequency FB. Yeah, FA actually, that is 100 Hertz. That is a unity gain frequency. So at 0 dB, when V out, that is your output of your practical differentiator, that is around, let's magnify it and let's check it thoroughly. Okay, this number is close to 100.89 Hertz. Okay, it is around very less value, but 100.89 Hertz is the frequency FA. Okay, now yeah, so I just want to show you all one thing now, that this diagram which you can see in the OneNote PDF, it's actually taken from here only. As you can see, it's the same diagram, and you can check it out. It is the, I've taken a print screen of this LT Spice window, and then I've written over here all the modification and suggestions, right? So whatever we are discussing over here, it's already been simulated. So this image which you see, it's simulated in LT Spice. I have just used this image as a print screen image and added the additional information. Okay, so let's concentrate on this OneNote PDF now. Let me expand it and make it in the full screen mode. Okay, so now your value of FA was given by the formula 1 upon 2 pi RF into C1. If you calculate this with a calculator, you will get FA close to 100.09 hertz, and the gain in dB. Okay, here we are considering f to be very small, which is zero point 0.1. We cannot consider it to be 0, so we are considering a very small value, 0.1 hertz. So f over here is 0.1 hertz, and 20 log to the base 10 f upon fa minus 20 log to the base 10 1 plus f upon fb the whole square. This is the formula. We substitute the values of f, fa and fb. Fb is from point number 10, which is given by 1 upon 2 pi R1 into C1, which if you work out in a calculator will be close to 1000.97 hertz. Okay, and yeah, the gain in dB, if you work it out in a calculator, the first term will give you minus 60 dB, and the second term will be very small. It will be negligibly small, hence we have considered to be 0 dB. You all are free to check it out, and the gain in dB will be 60 dB. So here it is the 60 dB point. Okay, wait a second. Here is the 60 dB point, which we got it in the LT Spice also. So this image is taken from the results obtained in the LT Spice. So this is 60 dB minus 60 dB, and as I've said earlier, informed earlier, the orange color curve is the open loop, the green one is the ideal differentiator, and the blue one is the practical differentiator circuit. And FA is marked as the frequency, as the unity gain frequency, where the gain of the differentiator is unity or 0 dB. So that frequency is coming around at 100 hertz. Okay, so this is the frequency response of a practical differentiator circuit. Now let's evaluate and make some observations from this equation number 3.A and 3.B, and this frequency response for the practical differentiator. So these are the equations. Equation number 3.A, 3.B, and together combined with this frequency response, we'll have quite a lot of observations. So the first observation is, from frequency f equal to 0.1 hertz to FB, the gain of the circuit increases at plus 20 dB per decade. Okay, so let us check it out. So here at the start we have 100 millihertz, that is equivalent to 0.1 hertz. So from here till FB, the gain of the differentiator keeps on increasing at a rate of 20 dB per decade. So that rate is called as roll-off rate. So how it is 20 dB per decade? Let's check this point. So at 10 hertz, we have a frequency of minus 20 dB, and at 100 hertz, we have a frequency of 0 dB. So rise in the gain is 20 dB, and this is happening at a 1 decade change in frequency. Hence, the roll-off rate is 20 plus 20 dB per decade. Okay, so yeah, it is true. The gain of the circuit increases at a constant roll-off rate of plus 20 dB per decade from 0.1 hertz to FB value. Now, for frequencies greater than FB, the gain of the circuit decreases at the rate of minus 20 dB per decade. Okay, so if you have any frequencies greater than FB, especially for a practical differentiator, which is the blue color curve. So as you can see, this blue curve is almost merging with this green ideal differentiator curve at a value which is lesser than FB, almost like lesser than FA. It will be almost matching and slightly deviating from FB onwards. So for any frequency beyond FB, that is around 1000 hertz, the gain of the practical differentiator starts falling down, and that rate of fall is constant, and that is given by minus 20 dB per decade. So here you can see over here the gain is around 0 dB at 10 kilohertz, and around at 100 kilohertz it's around minus 20 dB. Hence the fall, hence the roll-off rate at after your frequency is greater than FB is minus 20 dB per decade. So that is practical differentiator for you. At high frequencies, it will reduce the gain. Okay. So there is a 40 dB change in the gain, which is caused by R1C1 and RF CF combination. So here it is plus 20 and here it is minus 20. So total change in the gain is 40 dB per decade. So from the frequency response curve, FA is the frequency at which the gain is unity or 0 dB, which is given by the formula 1 upon 2 pi RF into C1. Let's check that. So FA is the frequency at which the gain of the practical differentiator is unity or 0 dB. So that is very, very evident from this frequency curve. Also, beyond FB, the gain of the circuit is limited, and thus the FB is called as the gain limiting frequency. And it is given by FB is equal to 1 upon 2 pi R1 into C1. So beyond FB, as you can see over here, if any beyond FB point, the gain of the practical differentiator is limited, right? That is why FB is called as the gain limiting frequency. That's what is written over here. Now, some observations. Point number 5 says that for an ideal differentiator response in green color, the gain would have increased continuously at a rate of plus 20 dB per decade, even beyond FB value, which causes stability at higher frequency. So here you can see clearly that ideal differentiator beyond FB point also, it's keeping on rising, and ultimately it is leading into instability. So that is the point which was discussed in point number 5. And point number 6 says that in case of a practical differentiator marked in blue color, the gain at higher frequencies is reduced significantly, thereby avoiding the high frequency noise and stability problems. So if you look at the practical differentiator, for higher frequencies, a gain is getting reduced at the rate of minus 20 dB per decade. So all your stability problem at higher frequencies, which was evident in the ideal differentiator, here you can see it's all avoided, and also the high frequency noise is also getting reduced by this reduction in the gain. So all these two problems are being taken care of by the practical differentiator circuit. Now, generally, the value of FB is selected such that FA is less than FB. That is, we make R1CF much larger than R1C1. So let's see this point. So yes, it is true. FA is 100 Hertz. FB is 1 kilohertz. So definitely FA is lesser than FB around by 10 times. So that is normally the term which is normally the trend which is followed. Okay. Point number 8 says that for a good differentiation, we must ensure that the time period of the input signal is larger than or equal to RF times C1. So that means, in short, for a good differentiation, we should consider the time period to be greater than or equal to RF times C1. So that's the point to remember. Now, point number 9 clarifies the design steps to be followed for a good differentiator circuit, for building a good differentiator circuit or designing it. So the first step is choose FA as the highest frequency of the input signal. Next is assume a practical value of C1 that is lesser than 1 microfarad and calculate the value of RF. Next step, you choose the value of FB 10 times of FA, and next calculate the value of R1 and CF such that R1 C1 is equal to RF CF. So that's what we do. So you follow normally these steps, and your design of your integrator will be in the right direction. Now the last point clarifies where are the practical differentiator used. Now, so they are commonly found in the wave shaping circuits to detect a high frequency component of an input signal. Moreover, they are also used as the rate of change detector in FM modulator. So these are two places where you can possibly use a practical differentiator. Okay, I think we have come to the end of this online session. So we have discussed today the circuit for a practical differentiator. We have analyzed the circuit and derived its transfer function. And we have also built up the frequency response of the system, analyzed each and every point, and we have simulated the same in the LT spice, and found that the results was inconsistent with the theoretical values. And later on, we also discussed few applications of a practical differentiator. So I guess that's it for today's lecture. Next time we'll start with the design for a practical differentiator. So until then, have a good day and thank you.